nobody to help. Anyway, uh, at least you
Yeah,
see my talk. Uh,
yeah.
yeah, this
Screen
is,
is visible clearly, sir. This is coming on correct way.
yeah, at least, we see, I mean, machines are still not smart enough. We always have to tell them what to do. Uh, I mean, they should be smart and fix me. I mean, but they are not, seems. They are not that
Yes.
smart yet. Maybe they will in the future.
Yes, yes, yes. Yes.
Okay.
Yeah,
Uh,
please.
so this is a talk. I'm not sure. I think I gave this talk maybe 3 months ago uh, on pseudo valuation domain. And I really enjoy, by the way, the talk by the number theorist. And I always say that if I'm not in commutative algebra, I will be a number theorist. And
Yes.
in fact, maybe this is not the time to mention it here. The the university I went to, they don't have a number theorist. Or since I was a kid, numbers always amaze me. And I mean, I cannot call myself number theorist, but from time to time I look at something that I can understand, because also number theory, I mean, like the first speaker about the arithmetic sequence, that's
Yeah.
amazing. That was amazing to me. I really like
Yes.
that. I really, really enjoyed that talk. It was I
Yes.
mean, for me, these things, I mean, maybe for somebody who's not specialized, I believe.
Many audience is motivated, sir, and they are appreciate all the talks.
Yeah, I mean, I really enjoy. I mean, I'm not saying the other two. I mean, here is the thing. When I speak, maybe I screw up myself. I'm not
Yeah.
saying the other talks are not nice. I'm saying, I think you get my point.
Yeah.
Yeah, okay. So maybe I should shut up and start my talk.
Sure, sir.
Okay, on n-pseudo valuation domain. This is with my long, since, I'm writing with David F. Anderson, maybe since, I don't know, 1999 or 2000. And here is another work with him, and that was published maybe 2 years ago. Uh, let me, I think you go to the next slide by doing arrow, right? Uh, I can move how can, yeah, here we go.
Uh,
Yeah, yeah,
yeah. Is
I see it, I see it. Okay, the story started in 1978 by Hedstrom and Houston, pseudo valuation domain. This is very old paper, and in that paper they generalize the classical valuation domain. So before I tell you what's a pseudo valuation domain, every valuation domain is a pseudo valuation domain, but definitely not every pseudo valuation domain is a valuation domain. And they gave these two papers here. And when I was in graduate school and things like that, we were looking at what others do, and this is, I think, that what we all do, when we are in a graduate school. So let me first thing, valuation domain, there are many definitions. The easiest, the simplest way of valuation domain, whenever you have two elements in the ring, then A is a factor of B, or B is a factor of A in the ring. One of them divide the other. That's a very simple definition of valuation domain, or even ring in general. Pseudo valuation domain Here is the definition. Of course, I am simply so you have an integral domain R, and you go to the quotient field K, and then you want whenever you have x, y in K in the quotient field, and x, y is in the prime ideal Q, you want x in a Q or y in a Q. Of course, I mean, you have to be careful here. We are not selecting x and y from R. Of course, then there is nothing there. Uh, we're selecting x and y from the quotient field of R. Okay? If every prime ideal satisfy this kind of this condition, then we call the prime ideal strongly prime. But for the time being, if I give you many definition and things, you get lost, because I do too sometime when there are so many definition. So for the time being, you think of a prime evaluation domain, pseudo valuation domain. You think of them where every prime ideal satisfy this condition. And remember x and y in K. There are many generalization of pseudo valuation domain. Uh, there is another definition that we need. This is by D.D. Anderson and Muhammad Zafrallah in 1991. They talk about almost valuation domain. Uh, if you have an integral domain with a quotient field k, then R we call it almost valuation domain if for every non-zero x in k there exists n depend on x, and that's very crucial because again I use this definition. You're gonna see it later, but for their definition of almost valuation domain, for every x in K, there exists an n depend on x, where x to the n in R or x to the minus n in R. Okay, how do you translate that to the language of elements in the integral domain R? Whenever you have, let's see, non-zero element in the integral domain R, A and B, we should be able to find an integer n, and this integer rely on A and B, positive integer, where A to the n is a factor of B to the n, or B to the n is a factor of A to the n. So this is how you think of almost valuation domain in terms of element in the integral domain R. Uh, I can see this article, maybe there are other, but this is the one because now with that many journals and online journals and it's become more difficult to keep track how this thing. Anyway, I saw this is like came to my mind on almost valuation that was published in 2015 by Mahdo Mimouni and I cannot even pronounce Moto. Recent, well, I don't know what recent mean anyway. Okay. And also in 2007, I studied pseudo almost valuation domain. And this is makes sense. How? Look, you have valuation domain, then you have pseudo valuation domain. Dan Anderson and Zafrallah study almost valuation domain. So what do you think? I mean, it seems natural somebody will think of pseudo almost valuation domain. So before I tell you what's all this about, Remember at the beginning, I told you pseudo valuation domain, generalization of valuation domain. Well, we have almost valuation domain. So now pseudo almost is a generalization of almost valuation domain. So before you know anything, almost valuation domain will always be pseudo, but pseudo almost valuation domain need not be almost valuation domain. And here is the definition. Of course, this is the equivalent, the easy one to deal with. Um as usual, R integral domain, and you take a prime ideal Q of R, and this prime ideal need to satisfy the condition that for every x in K, there exists a positive integer n such that x to the n in a Q or x to the minus n a in a Q, and here is missing a is an element of the ring R for every a in R. Okay, let me think of the, yeah, or x to the minus n a. I think here a, I need it to be non-unit. I have to check that. It's been a while, but I think a can be any. Uh, yeah, x to the, for every non-unit a, it has to be, because otherwise I think you will have valuation. Yeah, a is a non-unit. I'm very sure now. For every non-unit element A of the integral domain R. Okay, so that's the definition of pseudo almost. Uh, Now let's get to the talk. And here we have to be careful. Remember in the definition of almost valuation, uh, n rely on the element x in the quotient field. You want x to the n in a Q or x to the minus n in a Q. Uh, Here we fix an integer n. Huh? So you fix it. Let we say I is n powerful ideal if whenever x to the n, y to the n in I, then x to the n in R or y to the n in R. Okay? And we say I is n powerful semi-primary ideal if whenever you have x to the n, y to the n in I for some x and y in K, then x to the n in I or y to the n in I. So here again, the difference in all these definition, here we're fixing n. So the same n has to work for such element. And this concept, by the way, myself and Houston study this powerful ideal called in 2002. Uh, anyway, let's see. Okay, so what is n-pseudo valuation domain? Okay, here is the thing. Before I tell you anything, if you let n equal 1, this will be the classical pseudo valuation domain. Okay? So we fixing an n and we studying like 2 pseudo valuation domain, 3 pseudo valuation domain. So to follow my talk, and you need to I think know really the definition of what we mean with n pseudo valuation domain. Abbreviation is an pseudo valuation domain. If every prime ideal is n powerful semi-primary ideal, every prime is n powerful semi-primary ideal. Well, if you want to remove the n powerful semi-primary ideal, it's easy to see that if you have a prime ideal Q and X and Y in K, then you have the condition X to the N, Y to the N in Q, then you need X to the N in a Q or Y to the N in a Q. Uh, you're going to ask me then, why did you introduce this here in Powerful? Well, if you see the paper, you know exactly why, because we study this class of ideals too, powerful and impowerful and so on. Okay, so I told you, if you let n equal 1, there is nothing new. Okay. So here is the first example, because we need to make sense of what we're doing. Like you take this integral domain, this is the D plus M construction. This is a very good method to construct examples in commutative rings. Or this is because sometimes, like you have, I have sometimes seen some theorems. Maybe the theorem is four-line, beautiful, and but you need one page to come up with an example, or two pages sometime. Uh, but the D plus M made the life of commutative algebraists a little bit easier to come up with examples. And this, of course, this construction rely on the power series thing. So Q is the field of rational numbers, and C is the complex. And you look at this, and of course you need to think and scratch. I mean, it's not much. But if you want the details, I will be happy to send you the paper. This definitely is not pseudo, almost valuation domain, and is not pseudo valuation domain. Remember, pseudo almost valuation domain, generalization of almost valuation domain. Uh, but in fact, you can check that this ring integral domain is for pseudo valuation domain. So that means that justify the work we're gonna do, because you need to find a class of domain that I mean, if you give me the same example, I mean, if the example I'm gonna give you is gonna be a pseudo valuation domain, so what? Uh, I think you get my point. So that was our first goal, to justify the work that really in pseudo valuation maybe it's worth studying this class of domain. Uh, okay, so there are some result here. Uh, okay, assume you have prime ideal P live inside Q, and Q is n powerful semi-primary ideal of R. Let me stop here and remind you again. You can think, or you forget this language here, n powerful semi-primary. It means whenever you have x and y in the quotient field of R, and x to the n, y to the n in a Q, then you need x to the n in q or y to the n in q. Okay? This is what n powerful semi-primary ideal. Then definitely the smaller one has to be also n powerful semi-primary ideal. If the bigger one is n powerful semi-primary, then the smaller one is. Well, what you get, then you come up with out of this result that if R is n pseudo valuation domain, then R has to be quasi-local domain. Quasi-local domain, by the way, I belong to the school of maybe Gilmer, Kablansky, and uh, they use it for integral domain with exactly one maximal ideal. I think many other authors they use local domain. But local domain for me means Noetherian and one maximal ideal. So anyway, and I think David Anderson and I know David Dobbs also use the quasi-local terms. But does not matter as long as we explain the language. So quasi-local domain does not mean Noetherian. It only means integral domain with exactly one maximal ideal. And by the way, also tell you this is also a similar result when all of us know that a valuation domain is a quasi-local domain. We know pseudo valuation domain are a quasi-local domain. And now this is like a generalization. You don't have to let n to be 1 all the time. You can talk about 2 pseudo valuation domain, 3 pseudo valuation domain, and these are, yeah. As I told you here, out of this theorem is what you see, corollary, that when you fix an integer n bigger or equal 1, then the integral domain is n pseudo valuation domain if and only if a maximal ideal of R is an n powerful semi-primary ideal. If and only if a maximal ideal of R is an n powerful ideal of R. Okay? So, uh, all right. It seems here I'm reminding you again with in semi-primary. Uh, okay, maybe here. Yeah, uh, here the n semi-primary for R. Because look, yeah, I remember now. This definition here uh, for the element in R, n semi-primary. Remember the previous one, n powerful. When you add powerful, you need x and y in k. When you if you don't have powerful, then you let x and y in R. And you can think of that as a generalization of the normal semi-primary. Why? Because what's the definition of semi-primary ideal? Whenever you have x and y in I, then x to the n in I or y to the n in I for some n. That's another way to think of semi-primary. Semi-primary, remember that the n depends on x and y. Here we're fixing n. So when you tell me I is one semi-primary ideal, then you know that your ideal is a prime, right? But when n is different from 1, then we are in a different situation. So you can study like 5 semi-primary ideal, where if you have x to the 5, y to the 5 in I, for some x, y in R, then x to the 5 in I or y to the 5 in R. Uh, and here is a nice result, I call it. If I is n semi-primary, then I is m semi-primary for every m bigger or equal n. The proof is not difficult, in fact, but some of these results, sometimes we mathematician, some of us, not all, like we look at like how difficult is the proof. And I am in the other school. Maybe I am in the school of Paul Erdős when he will, tell you straight from the book. I mean, some result, the one I love, that's of course my personal point of view. It's just short and, but sometime, of course, you cannot. You have to, write too much to do things. Anyway, so this result is very nice, but the proof is maybe 2 lines. So if you have an ideal that 3 semi-primary, then you know it's going to be 4, 5, 6, whatever. You only need, okay. Uh, Here are some examples I have. And again, by the way, all the examples in this paper are using the D plus M construction, uh, which is, I find it very powerful tool to construct examples in commutative algebra. Uh, Here are some examples like you can read. It's 2 semi, this m is here, fx squared plus x to the 4, add the power series, f double bracket x. Uh, this is 2 semi-primary, but not a 3 powerful semi-primary ideal of R. Because you're gonna tell me, does semi-primary imply powerful? No, it's not like 3 powerful. So uh, here is something. This m here is gonna be 2 powerful if and only if the characteristic of the field F is 2 and m is n powerful. M is an n powerful. Okay, so this is what's going on here. Uh, very, I always, of course, everybody like their work. This is kind of interesting because it's very natural. You're gonna tell me, does semi-primary implies powerful semi-primary? No. Okay. Anyway, in fact, an easier example than that, not every prime is a strongly prime. But anyway, okay, so then we come to another definition of divided prime. Uh, Divided prime, the first time I saw it was by a paper by David Dobbs. Uh, and then I generalized again, it was on integral domain. I generalized the concept for any commutative ring, divided. Divided prime, just let n equal 1. That's the meaning of divided prime. So I don't have to give you the definition. Divide, if you remove the n and you let n equal 1, this is exactly the definition of divided prime. Uh, n divided prime means x to the n is a factor of b to the n for every x in R but not in P. Okay? Uh, this is the definition of n divided. And remember again, in all these talks, n is fixed. It's not for some n. It's like you want x to the n to be a factor of b to the n. Okay? All right. All right. Here is a result. Uh, R is a pseudo valuation domain if and only if R is an n pseudo valuation domain. If your integral domain is root closed, what root closed? Well, let me remind you that x to the n in R imply x in R. That's what's root closed. And x from the quotient field of R. So I repeat, root closed mean if you choose x from the quotient field of R and you have x to the n is in R, then x has to be in R. If your integral domain is root closed, then there is no difference between these two definitions are the same. Like if you tell me three pseudo valuation domain, it's gonna be pseudo valuation domain. Of course, one direction imply the other. Does it? Let me think. I'm not a quick like you guys. So I'm very slow mathematician, by the way. It's known about me. Maybe what takes some of you a second, it take me minutes. Uh, uh, anyway, so these two concepts are the same. Yeah, definitely. Pseudo valuation domain implies n pseudo valuation domain, but definitely n pseudo valuation domain need not to be pseudo valuation domain. But in case your integral domain is root closed, then there is no difference at all between the two definitions. Okay, I told you about this. Yeah, here's a nice result. You're gonna tell me what's gonna happen to the quotient. Uh, R mod P, the factor ring. If you have a prime ideal of an n pseudo valuation domain, then definitely this one will be n pseudo valuation domain. Okay? Uh, I told you about almost valuation domain. I already gave you the definition earlier. Remember again, maybe I'm reminding you again. Almost valuation domain means whenever you have non-zero x in K, there exists an integer n where x to the n in R or y to the minus n in R. And again, remember that n depends on x. So what do you think our definition will be? We fix an integer n and we call R n valuation domain if for every non-zero x in K we have x to the n in R or x to the minus n in R. Okay? So you have an integral domain R and you fix a positive integer n. And so the difference between almost valuation and n valuation, the almost valuation, the n depends on the x. Here you fix an x. So I think here is some comment. N valuation domain definitely gonna be almost valuation domain. But trust me, the converse is not gonna be true. We constructed almost valuation domain that is not n valuation domain for some n, because otherwise, so these two are not equivalent. Okay. Uh, Here I made, I don't know, comment. Okay. Yeah, as what I told you. How many minutes left for me?
Yeah, sir, 5 minutes more.
Okay, I think I will. These are just some examples I told you. I mean, we just put them on the screen. I'm not sure how fast you can get them, but you know, this is, uh, I don't know. Anyway, as I told you, if you are interested, I will be more than happy to send you the paper because I'll be honest with you, uh,
Yeah,
I cannot really even.
yeah, right,
Anyway,
right.
okay. Maybe there is some nice result here. Like here is one. If you choose R to be n pseudo valuation and you have an overring of R where 1 over S in V, you have an overring. An overring mean a ring between R and the quotient field. Then this overring is going to be n valuation domain. Yeah, if you have n pseudo valuation domain and you have this element 1 over S in V, then definitely, yeah. Okay, and here is another one, and so on. Okay, here is some characterization, like the following are equivalent. R is n pseudo valuation domain. This is equivalent to the integral closure of R is a pseudo valuation domain with this maximal ideal, and is a maximal ideal of and n colon n is a valuation domain. Okay. All right. I already gonna end it, and I thank you very much. Thank you for inviting me, and you know, I always mention I am a regular customer to India, and I'm still waiting for my citizenship because in the old days I used to go to India 4 or 5 times a year. And anyway, thank you.
Yeah, thank you very much, sir. All your talk are motivating us, sir, too much.
Well, thank
That's
you.
why we are, yeah, that's why we are also already, you have to, we have any chance to invite you, then definitely we are call you first.
Thank you.
Yeah. So here, any question or comment?